Hello and welcome. In this video, we're going to find the probability of disjoint and overlapping events. And our objectives are I can find the probability of compound and mutually exclusive events. I can find the probability using the addition rule. So let's go ahead and jump in. Let's start, as usual, with some vocabulary. We're going to be using this Venn diagram off to the right to really make sure we understand what these words are. So when we're talking about event A, that's going to be this side of the Venn diagram, and event B is going to be this side of the Venn diagram. So our first vocabulary word is union. When you consider the union of all outcomes, you're talking about something in A, B, or in both. So really, it's everything included anywhere in the Venn diagram. So it could be just in A, it could be just in B, or it could be in both. So looking at these numbers, it could be 1, 2, 3, 4, 5, 7, 9. All of those are either in A, either in B, or in both. But either A, B, or both. That's the key idea there. The intersection is exactly what you would think. I think intersection, I think of driving in a car. I think of where a stoplight is, where multiple things meet. So the intersection is going to be the numbers only in both. So in this case, on our Venn diagram, the intersection would be 1, 3, and 5. A compound event is just the union or intersection of two events happening. So for example, if we think about a deck of cards, a compound event could be that we pick a 2 and that we pick a heart. So multiple things happening at once. Two events are overlapping when they have one or more outcome in common. So thinking back to this 2 of hearts, if I said a 2 or a heart, there is an overlap because there is a card that is both. The card that is both would be the overlap. So the 2 events would be 2 or heart, and the overlap would be the 2 of hearts. So 2 events are overlapping when they have one or more outcome in common. And the opposite of that is 2 events are disjoint or mutually exclusive when they have no events in common. If we're thinking back to a deck of cards, if I said a 2 or a 7, there's no card that is both a 2 or a 7, so those would be disjoint or mutually exclusive. And don't worry, we're going to look at many examples, including these vocabulary words, and we're going to look at the notation of how we write these things out. So now that we've defined some of our vocabulary, let's talk about the big idea in this section, which is the probability of compound events, or the probability of mutually exclusive events. But probability is our big topic here. And something I want to point out is that this first box says, if A and B are any 2 events, then the probability of A or B, probability, which we're going to write, probability of A or B like this, is equal to the probability of A plus the probability of B minus the probability of both. So overlap. So in the example that we talked about before, we would say the probability of 2, the probability of hearts, minus the 1 card that happens to be the 2 of hearts. That would be our overlap here. Now, if there's no overlap, meaning if the events are disjoint, then this probability would just be 0, which means we don't have to include it over here in our formula. So this is really the same formula, just listed out in slightly different ways. If we know they're disjoint, then we don't have to subtract anything off. So the probability of A or B is just the probability of A plus the probability of B. So in the card example, we talked about the probability of 2 plus the probability of 7. Before we get to some concrete examples, let's quickly go through a notation, and then we can look at some examples. All right, here we go with our notation. So we talked about union, meaning everything inside both. So anything in A, anything in B, anything in both. What the notation for that looks like is the union is sort of like a U symbol. It looks a little bit fancier, but A union B, that's how we would read that out loud. And what that means is everything in both sets, which means I could just highlight over the entire Venn diagram. So the notation you're going to use, you're not going to write the word union, you're going to use the symbol U for union. If I flip that U upside down, I get the symbol for intersect. So A intersect B is how we would read what we're looking at here, A intersect B, and that's just what's in both sets, and in here that would just be this middle piece. One thing we haven't really talked about, but we are going to use in this is a complement. A complement is the opposite of something else. So you will commonly see it used as A prime with the little apostrophe, or as the bar above it, A bar. And what that means is everything that is not in set A. So let's pretend we were talking about rolling a die. And if we rolled a die and set A was all of the odd numbers, A complement or A prime would be all the even numbers, because it would be all the numbers that are not in A. And we'll look at that more, and you'll see how that's helpful when we get to some examples. So let's get to some examples. All right, here we go. For this first set of examples, we're going to be looking at a random deck of 52, standard deck of 52 playing cards. And we are going to be randomly selecting a card, just one. So question 1 says, what is the probability that it is a 10 or a face card? So the probability that it is a 10 or a face card is going to be the probability that it's a 10 plus the probability that it's a face card minus the probability that it is both. In this case, if we think about a deck of cards, there is no 10 that is a face card. So these are disjoint events, and we don't need to worry about subtracting out the overlap because there is no overlap. So if we're going to find this, the probability of a 10 or a face card is going to be the probability that there's a 10. So out of the 52 cards in a deck, 4 of them are 10s. Of the 52 cards in a deck, the face cards, the ones that have a face, queen, jack, king, there are 3 in 4 suits, so there are 12 of them. If I add these two together, I'm going to get 16 over 52, and we always simplify our fractions. And if we simplify that fraction, we can divide both of those by 4. We're going to get 4 over 13. For number 2, what is the probability that the card we draw is a face card or is a spade? So the probability that we have a face card or a spade is equal to the probability that we have a face card plus the probability that we have a spade minus the probability that we have both. I'm going to come down here so I have more room. Actually, let me clean that up. That's better. So the probability that we have a face card or a spade, and notice I'm keeping my work in line so it's easy to follow. Well, we already talked about on number 1, the probability of having a face card is 12 out of 52. The probability of having a spade, there are 4 suits and one of them is spades. Since I kind of just want to keep everything as a common denominator, instead of writing 1/4, I'm going to write that there are 13 of the 52 cards are spades. You could also write that 1 of the 4 suits are spades. That would work as well, but that's going to make it harder to add these two fractions together. The probability of both, that we have a face card or a spade, how many of the face cards are spades? Well, 3 of them. 3 of those 52 are spades. Now, if we add and subtract these fractions together, we're going to keep that same denominator of 52. 12 plus 13 minus 3. 13 minus 3 is 10. 12 plus 10 is 22. And as always, our final answer is going to be a simplified fraction, which in this case, if I divide by 2, is going to give me 11 over 26. Now that we've done a couple of examples together, I'm going to encourage you to pause the video and work through numbers 3 and 4 on your own, and then unpause the video and see how you did. Hopefully you've had time to look at these. Find the probability that we have an ace or an 8. That's going to be the probability that we have an ace plus the probability that we have an 8, and there is no overlap, so we're not going to have to subtract anything out because there's no card that is an ace and an 8. The probability that we have an ace is going to be there are 4 aces out of 52 cards. There are 4 8s out of 52 cards. That's going to give us 8 out of 52, and then we're going to simplify that fraction by dividing both of those by 4. So the probability of drawing an ace or an 8 is 2 out of 13. Looking at number 4, find the probability that we pull a card that is a 10 or a diamond, and this time we will have overlap because there is a card that is the 10 of diamonds. So the probability that we have a 10 or a diamond is going to be the probability we have a 10 plus the probability that we have a diamond minus the probability that we pull the 10 of diamonds. So the probability that we pull a 10, there are 4 out of the 52 cards that are 10s. The probability that we pull a diamond, 13 of the 52 cards are diamonds. And then we're going to subtract the 1 card that is both. So that's going to give us 17 minus 1, 16 over 52. And then we're going to simplify that fraction. And when we simplify that, dividing both the numerator and the denominator by 4, we get 4 over 13. Now let's look at some other examples that don't relate to a deck of cards. All right, here we go, number 5. Out of 200 students in a senior class, 113 of them, so 200 is going to be our total, 113 of them are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. So I'm actually going to organize this information in a Venn diagram just to help me visualize what's going on. Okay, so the total number of students, I'm going to just make note to myself up here. There are 200 total students. 113 of them, I'm going to highlight over my circles in blue so you can see them. 113 of them fall somewhere inside the circles, whether it's on the left in the red circle for varsity athletes, on the right in the green circle for honor roll, or in the middle, both. 113 is that number. So I'm going to put this and I'm going to write 113. Just again, helping myself organize this information. There are 74 that are just athletes and 51 honor roll. I'm going to abbreviate that HR. If there's 113 that fall within the circles, 200 minus 113 means there's 87 that are outside. There are 87 students that are not an athlete or on the honor roll. So now that I've organized my thoughts, I'm going to look at the questions here. A says, what is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? So it's asking us, what's the probability that a student falls in this region here? So we know that the probability that a student is an athlete or on the honor roll is equal to the probability of being an athlete plus the probability of being honor roll minus the probability of both. And our goal is actually to find the probability of both. So we want to solve, this is the piece of information we're trying to find. And we know the other pieces of information. We know that of the 200 students, 113 of them, so this is 113 out of the 200. We know that 74 of them were athletes, so that's 74 out of the 200. And that 51 out of the 200 were on the honor roll. And now, after we plug that information in, we really just need to combine these and subtract that number on both sides to figure out what the probability of both is. So in this case, the probability of both, 113 minus 71 minus 51, that's going to give us 12 out of 200. And as always, we're going to simplify that fraction. We can divide both of those even numbers by 4, actually. That's going to give us 3 out of 50. The probability that a student is both an athlete and on the honor roll is 3 out of 50. So for part B, we're still using the information about 200 students, 113 being varsity athletes, 51 being honor roll students, but we're going to be given some new information. So part B says, suppose 32 seniors are in band and 64 seniors are in the band or honor roll. What is the probability that a randomly selected senior is both in band and on the honor roll? So go ahead and try and set this up on your own. You can draw a Venn diagram if you would like and work through it and then unpause the video and see how you did. So if we put our information out there and then we pull these numbers from the problem itself, now we just need to figure out what the probability of both is. And that's going to be 19 out of 200. All right, we're going to extend this idea to sort of add a bonus to challenge those of you that like an extra challenge. We're going to look at the probability using the addition rule or having more than one probability going on. That's going to be our very last example, and then we will wrap up this video. So in this lesson, we specifically focused on finding the probability
a little bit
if
further.
events are disjoint.
In this chapter,
we learned a
if
lot
they
of
are
different ways to find
dependent. But
probability.
let's tie this
Sometimes
back to
dependent,
what we have been
sometimes
learning. This whole
independent.
chapter has been about
And
probability.
this last example is
in
gonna
other
tie a bunch
sections,
of
we
things
focus on
together.
different
I don't want
probability
you to
rules.
worry
We
too
talked
much
about
if it's a challenging one. That's the
something
point.
is
It's got to be
given
pushed a little bit
versus if
sometimes.
it's
So
not
we're going to
given
work
or
through
this
multiple
together.
events happening at the
Number
same
6
time.
says
And
the
we're going to
American
tie those
Diabetes
ideas
Association
together in this one last example just to push our understanding a little
people
further.
in the United States have
The
diabetes.
solution or the reason behind this is because in
Suppose
real life
that a medical
problems,
lab
we
has
often
developed
have more than
a
one
simple thing or more
diagnostic
than one piece of
test for
information
diabetes that's
impacting
98%
our decision.
accurate for people who
So,
have
last example,
diabetes.
the American
And
Diabetes
95%
Association
accurate for people
estimates
that
that
do not. 8.3% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for the people who have the disease and 95% accurate for the people that do not have the disease. The medical lab gives the test to randomly selected people. What is the probability that the diagnosis is correct? So the very first thing I want you to do is pause the video and just highlight the important information here. So I've highlighted. I'm also going to just come off to the side over here and I'm going to write brain dump and I'm going to just put down what I'm reading here. These are given as percentages and we want them to be decimals so that we can work with them. So when it says 8.3% of people have diabetes, what that means is the probability of having diabetes is 0.083. We move that decimal place twice, and the probability of not having it would be D prime, or you could say D bar. That would be 1 minus this value, or 91.7%, which we're going to write as 0.917, right? Because these two numbers have to add up to be 1. The second piece of information they told us is 98%, the test is 98% accurate for people who have the disease. So given that they have the disease, the probability of it being accurate. So the probability of it being accurate given they have the disease, that is 0.98. And the last piece of information, the probability that it's accurate for people that do not have the disease is 0.95. So that's just sort of organizing all the information here. Our goal is to find the probability that the test gives the right diagnosis. But there's two situations that can happen here. First, we could be testing someone that does in fact have diabetes. So the probability that we test someone that has diabetes and that the test is correct, we're going to multiply that by the probability that they had it and it's correct. So this is basically yes, yes, they have it and the test gives the correct results. We're going to add that to the probability that they don't have it, they don't have diabetes, and that we get the correct result from that test. So A, given that they don't have it. So this is no and no. So we're basically saying what's the probability that we're right? Probability that the test gives yes and yes, the test gives a yes and they have diabetes, or that the test gives a no and they don't have diabetes. That is how we would find the probability that the test is correct. Now we just need to fill in the values that we've already listed in our brain dump over here and simplify to find our answer. And there we have our simplified problem. I actually am also going to just quickly go ahead and write a sentence that says the probability the diagnosis is correct is 0.952 or 95.2%. All right, and that is the most challenging problem of this entire unit. So I don't want you to worry too much about that. Know that it was just a fun way to kind of summarize everything that we have learned. So let's go ahead and wrap up this video. All right, our goal in this lesson was that we would be able to find the probability of compound and mutually exclusive events. We focused on that with the card problems. We looked at different populations of seniors and the different activities they're participating in on campus. And lastly, we talked about finding the probability using the addition rule, where we have different components from the entire chapter coming together. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.